So welcome to this week's seminar series for changing electric energy systems. Today we have Mads R. Almassalkhi presenting. Mads is an associate professor at the University of Vermont with a joint appointment at Pacific Northwest National Lab as chief scientist. He received his PhD from the University of Michigan in electrical engineering, and his research interests lie at the intersection of power systems, mathematical optimization, and control systems, and a focus on developing efficient algorithms that improve responsiveness of energy and power systems. Mads is also the co-founder of clean tech startup Packetized Energy, which was recently acquired by the largest demand response provider in the US. Mads, thank you for joining us. You can go ahead and present.
Thanks for having me, Daniel, and thanks for the invitation, Maria. Good to see you in the audience. It's too bad I'm not there physically, but next time. And so thank you everyone for joining me today. And as I'll share some of the experiences and results that we've had in our group, looking at grid flexibility and what I would portray as kind of a battle of sorts between control architectures, information scenarios, and how to implement grid optimization in a meaningful manner when it comes to distribution systems. And some of the work I'll present today, I didn't do alone. I've had the fortune of having lots of fantastic collaborators, both within Vermont and abroad and across the US, including students who've largely contributed to most of the work I'll present today. And at UVM, it's not just myself working on energy. We really have an interdisciplinary group looking at energy and autonomy, more broadly looking at autonomous systems, resilient systems, and how to leverage control and optimization tools and how to develop methods that really allow us to enhance specifically energy systems, but also more broadly, all kinds of systems. And so we have a group with a pretty broad expertise spanning social science, mechanical engineering, electrical engineering, and complex systems. And we've been fortunate not just to work, with our students, with our colleagues, but also with, funding partners and industry supporters. And it's been really an exciting experience at UVM to be able to kind of extend beyond the boundaries of academia and really poke and prod both industry and federal partners. And then beyond the academic communities, beyond the industry partnerships, we've also been able to spin out some of our research to actually, found companies and then have those companies be acquired. And what that means is that the technology that we've been working on in labs, technology that our students have kind of worked with us on, has actually been able to achieve access to scale through our recent acquisition with Energy Hub, where some of the technology that was, printed on physical papers in the 2010s has now been basically submitted to the ether and has access to 1 million devices. I'm not affiliated with Energy Hub, and I'm not going to sell you anything regarding Packetized, but bringing research from academia, from papers into products is something that I think is an extremely fun and very rewarding experience. And a part of being able to do that is in part because the state we're in is really a fabulous platform when it comes to power and energy R&D. In Vermont as a whole, with relatively small, power systems, we're relatively, a 1 gigawatt system is fairly small. It's a small state, but per capita, Vermont really knocks it out of the park. And so there are lots of fantastic stats I can give you, kind of showing how University of Vermont benefits from being in a state that really pushes the envelope when it comes to clean energy integration, workforce development, and surprisingly solar PV. And the policies across the state actually helps kind of push our way of thinking as well, both on the industry side with utilities, transmission operators, but also in the academic discussions. And so these are some of the fun things happening within the state. And the last thing I added was the electrification of electric aircrafts, which are taken off in Vermont through a company adjacent to the energy industry, which is Beta Technologies. Speaking of other things I will not talk about, some of the things I will not talk about today are optimal network reductions, which is a problem that we've recently been working on and find very interesting. I will not talk much more about packetized energy management, not specifically about it at least, We also have done a lot of fun work with NASA looking at trajectory optimization of small satellite systems. And then we have some new work kind of looking at how to characterize and measure the different DER algorithms that are out there in the academic literature, and trying to compare and contrast algorithms by measuring their communication overhead, or their ability to cycle devices, or their ability to deliver energy to people. So I'll skip some of those works as well today, but happy to talk offline or separately at a different time. Something I will talk about today, however, is the fact that the green economies across the world, around the world, is rising. And when we say green economy, I mean very broadly, environmental, low carbon, and renewable energy activities. And so we see, large sales revenue being tied to large number of jobs being supported by this green economy. Beyond this, there are, of course, massive venture capital investments being made in all kinds of climate technologies. And so it's an exciting time for the green economies. And it's really a rising wave that we expect will continue growing for the next decade. But with the rising wave of the green economy, there's also significant climate challenges. And so we're at a point where inaction is inexcusable. And so we're looking for solutions. And some of those solutions, if we find solutions and they work, we know they will matter. And so it's a very impactful area to work in at the moment. And what was pretty clear, I think, across the board is that we need terawatts of renewable integration. And terawatts of renewable integration represents a massive power systems challenge. And so we're really, power engineers who went through the 80s, the 90s, and 2000s, we're really changing the way we think of power engineering into becoming climate change engineering, or mitigating climate change. And so we're really looking at as an academic, looking at our solutions having a global impact. And again, it's an extremely satisfying place to be in at the moment, because we feel like we can have an impact and we can make a change. And so one of the areas that I work on is really looking at how we can leverage flexibility to help integrate those terawatts of renewable energy. And at the core of kind of flexibility to integrate renewables, we're really looking at electrification, which recently, through public policies, have really pushed both grid operators and deployments and electricians and a large portion of the US green economy into kind of limitation, into kind of very exciting space. And so we're looking at leveraging electrification to improve both efficiency of older devices, but also to electrify end use so that we can absorb more renewables. And better yet than just absorbing renewables or being more efficient is really about enabling the devices to modify their behavior, so to slightly defer their demand so that they can absorb energy at the right time. And that can help mitigate the duck curve, or was it the canyon curve now, to improve ramping effects. And we're seeing that with batteries as well today. And so it's exciting when you listen to the Department of Energy, or you listen to politicians, or you listen even to your local utilities talking about how we're going to go from kind of classic demand response in the 50 gigawatts or so range to become 200 gigawatts of flexible demand within a couple of years. And so we're 6 to 7 years away from this 2030 deadline. And so there's lots of opportunity, and with that comes lots of opportunities to coordinate, or the need to coordinate, billions of energy resources. And coordinating billions of devices is very different than the energy system we had 20 years ago, when you had hundreds or thousands of generators. And so the simple idea behind flexible demand is really to take all these electric assets that are going to be deployed, such as electric vehicle chargers, residential batteries, air conditioning loads, or electric water heaters, and basically connecting them through cheap wireless sensing, a technology that's widely available, ubiquitous, and most new electrical appliances have these installed already. And so by combining communication systems, control systems, and demand side or behind the meter energy resources, we can really aggregate these devices. And so individual homes, neighborhoods, towns, or even an entire state can be thought of and become a dispatchable resource. And so now we can stop the presentation, we can take questions and say, we did it, we're done, we know how to do it. Even companies will agree with us that there's significant value in kind of pursuing these aggregation strategies. And so you see lots of products available today called virtual power plants, or virtual batteries, or prosumer devices and technologies. And all of these technologies are in some way accessing different types of values in the entire electricity industry. So there are ancillary services that can provide revenues you can arbitrage around wholesale energy market prices. You can even provide peak reductions at the right times to avoid basically capital expenditures associated with T&D or generation assets. And so you're seeing lots of companies today kind of proposing all these new aggregation technologies as a way to support either utilities or wholesale markets. And that means that we're at a place where we can really talk about DER coordination as becoming kind of this real-time, flexible, adaptive, responsive asset that's being provided by certain aggregators or technology companies. And so the question becomes, if you are a DER coordinator or you're an aggregator, what do you know and what do you control? And we know that DER coordinators have access to the DERs, behind the meter loads, for example. They can send control signals to those loads to change their behaviors. And we know that at scale, that physical coupling is something that grid operators can see on their grid. But the grid operators don't control those devices directly. And so the grid operators are very good at understanding grid data. They're very good at understanding how to manage their grid, at least when they control every asset on it, or at least every major asset on it. And so there's this question of who knows what and who can control what. And that at the moment sets aggregators and utilities up as kind of oil and vinegar. They don't mix very well because there's no clear understanding of what data should be shared between aggregators and grid operators. Certainly you have software solutions like DERMS providing an avenue to share certain data between them, but there's no clear path as to who knows what and who controls what. And that's, of course, a very important question, because if grid operators want to provide a reliable grid, they kind of need to know what's happening at scale. DER coordinators, on the other hand, have customers who need energy for certain purposes, whether that's thermal management in their homes or electric vehicles, so people can go to their job or whatever it is they need energy for. And there are certain markets with which aggregators earn revenue. And so if they have built market business models around the ability to participate in those markets, and grid operators see risks associated with their reliability, then there becomes basically a conflict between who controls what and who knows what, and how will aggregators and their actions impact the grid, and how will the grid operators respond to grid aggregators or DER aggregators control actions. And so what I'll talk about today is kind of the bigger picture of who knows what, who control what, and what can we do. And so we've worked the last couple of 5 or 6 or 7 years looking at kind of DER aggregation, looking at controls, looking at flexibility, and providing certain solutions that allow grid operators and DER aggregators to emulsify and really form a more what do we want to call it, a more healthy relationship. And so I'll try to propose some of that today. And before we get too far, let's just briefly talk about flexibility. So I think I promised earlier that there's value in the kilowatt flex. And so that's the flexible capacity of certain loads. And so when it comes to loads, it's complicated. When we talk about a battery that stands alone for grid purposes, it's fairly straightforward to talk about flexibility. And some of the key parameters for battery's flexibility is, for example, its state of charge, its ramp rate, which is the ability to change power, its net injections, and its capacity. And so when we talk about flexibility, what we really talk about is, what's the magnitude of a power deviation? What's the rate at which we can respond to changes in power, and for how long can we sustain that power? And so when we talk about batteries, it's fairly straight. A single battery is fairly straightforward. When you talk about a heterogeneous mix of distributed energy resources or loads, it gets fairly complicated. And so, loads have humans as their users, right? My electric water heater or a heat pump or a thermostat or an electric vehicle is kind of driven by the human use. And that represents stochastic end uses. And so you can do all kinds of cool modeling around how to estimate background end usage. You can do really neat modeling and control of these aggregate populations. And in the end, you can kind of characterize some kind of a virtual battery or some kind of a resource that has certain stochastic characteristics, or effectively you have a stochastic battery in the end. And so this uncertain resource is something you'll want to dispatch in aggregate, potentially against wholesale energy markets. And so we've had a lot of experience kind of working through these aggregations. We had a field trial that looked at 150 loads in 2019, where we showed that we could effectively shape the aggregate behavior of 150 loads to deliver a certain grid service that was prescribed by the Department of Energy's Advanced Research Arm, ARPA-E. And we can also show through various analysis and various papers that the dynamics of that aggregate really depends on the control architecture, depends on parameters of that control scheme, and it depends on how the end users are responding at any given time. And so you have this time varying, fairly complicated blob that you want to characterize, model, and dispatch. And so simple questions like, how many devices do I need to provide a megawatt of flexibility or a megawatt of frequency regulation is surprisingly complicated. And because end use behaviors, constraints, the controllers all affect what that fleet can do. And so even something as simple as taking 500 batteries to track a frequency regulation signal is not super straightforward. And if you have 500 batteries, they perform differently than 1,500 batteries, and they perform differently than 3,500 batteries in terms of tracking a plus minus 1 megawatt frequency regulation signal. And so if you get paid for performance, you have to think about how many devices you need to earn sufficient credits for a 1 megawatt capacity payment from frequency regulation. If you then look at electric water heaters, it becomes very difficult because you're not only looking at the number of devices, but you also need to think about the time of day, because people use electric water heaters differently during different times of day. And so the amount of flexibility available from that fleet changes over time and changes from hour to hour. And so you can see that in some hours, you'll need around 10,000 water heaters to support a 1 megawatt frequency regulation signal. And at other times, it's 4,000 to 5,000 electric water heaters to support that plus minus 1 megawatt of frequency regulation. And so the time of day matters, the number of devices matters, and the duration over which you want to provide frequency regulation matters. And so if you want to participate in 2 hour blocks at a time or 4 hour blocks at a time, you have less flexibility per device compared to a 1 hour participation. And so it's a fairly complicated question, even though this question itself sounds quite simple. And so how many devices do you need really depends on a lot of things. And one of the core things it depends on is really your coordination architecture. So how are you setting up your control scheme? How are you controlling the DERs, and what are you measuring, estimating, or assuming? Certainly in the academic literature, that's the case. And so we see lots of kind of papers that have a lot of practical scenarios are implemented as direct load controls, such as classical demand response, where you kind of push on-off signals and devices turn off for certain periods of time, and then they come back online at different times. Or you have scenarios where you change the temperature thermostats, which are also fairly complicated, and these to do well. There are lots of top-down schemes, so we call them top-down coordination, where you some kind of broadcast a control signal out, and then you assume you have some kind of estimate, an external estimate of the synchronized response of the fleet that you feed back to some kind of reference tracking controller. In blue, you have what's called the bottom-up coordination schemes, where the devices can make asynchronous communications with the coordinator, and the coordinator can then determine the response to individual asynchronous communications, such as a packet request or a fitness value, and then turn on or off individual devices. Since the coordinator is in the bottom-up coordination scheme, effectively can manage each interaction asynchronously, it can build an internal estimate of the aggregate population and does not need to rely on external estimates, which is what is required for top-down coordination schemes. And so top-down has this external requirement, whereas bottom-up coordination schemes sidestep the external requirement and can build pretty accurate internal estimates from asynchronous communications. And so to give you some examples of one of the architectures, which was the top-down architecture or the broadcast-based approach, you can kind of see it sketched out here, where the megaphone is effectively your coordinator broadcasting the control signal to the DERs, and the DERs then responding in some way. That response could be randomized through some kind of stochastic control scheme, which is fairly advanced and has been implemented in the past. And the challenge with broadcast control schemes is that when you broadcast out the controls without knowing if the devices act upon that control or not, it's difficult to estimate internally what the devices are doing, and so you need to rely on some kind of external feedback. In addition, you don't know if the devices are in a position to respond or not, because there's no feedback from the devices themselves. And so you don't really know if the devices are responding at all. And so without that external feedback, it can be quite, it's an open loop schedule, basically, which is not necessarily a great thing for grid services. And with the feedback, you're assuming that you somehow have access to a substation or a frequency measurement and have enough penetration of devices that they affect the frequency itself, which may or may not be a practical assumption. And so one example of direct load control is kind of this 2,000 electric water heaters in Vermont as part of a local demand response program. And you can see this 3-hour period where they turn off all the devices. So they broadcast an off event, all the devices turn off, and then 3 hours later, they allow the devices to come back on. And you get this synchronized cold snap response. And then through heterogeneous usage from end users, you essentially see the population mix itself back up and kind of return to normal again. And so we know from control systems, we know from optimization that we can do a lot better than sprinkler control. And that's why it's also kind of funny to look back in time and see, what kind of creative, inventive schemes were implemented, in I guess it's 40 years ago now. And so there was this demand subscription service where this was, SCE, Southern California Edison, effectively asked people to volunteer to sign up for a certain amp or a certain fuse that had a certain limit. And this fuse meant that during an event, when a broadcast was made, the human had to run around the house and turn off assets, devices, until their current consumption, power consumption, was within the fuse limit. And then during the entire event, they have to stay within the fuse limit, or they would effectively have a blackout. The devices would hit the fuse and you would have no power in your home. And so this human in the loop implementation is quite clever. And it didn't last too long because it's not in use today. But you still see utilities today kind of sending or keeping the human in the loop by sending lots of SMSs. And so companies like OhmConnect kind of built out of those ideas and took the SMSs to another level, and really did actually show pretty good adherence to the policy, because the California market for SRAM was very favorable and provided a very good incentive for consumers to respond. Another scenario is when it comes to electrification is the electric vehicles. And so electric vehicles, if at scale and at a large integration, will threaten certain transformers. And so if we assume that the small pole-top transformers can be replaced before any issues occur, then you sit with this, MVA scale substation transformer. And distribution level substation transformers are expensive, they're hard to replace. And so you would like them to basically stay as long as possible. And so with lots of electric vehicles, you risk the chance of overloading the transformer. And if you overload it repetitively, you effectively wear down the installation, and then you end up with certain disasters, or at least grid failures. And so to overcome it, you could think of more dynamic ratings for transformers. You could model it. You can basically build thermoelectric models of transformers. You can manage the currents of the individual electric vehicles, and then do some kind of optimal control scheme to implement it. And so if you are in the world where you assume you have full information on the electric vehicles specs, the electric vehicles objective functions, and the transformer specs, and the transformer measurements, you could solve an open loop optimal control problem where you effectively allow the devices to charge as quickly as possible, limit wear and tear on the batteries, and effectively broadcast out some kind of a receding horizon implementation. And you can show that that works fairly well. There are lots of nice, convex optimization challenges hiding in there because the temperatures are nonlinear relationship with the current. And so you end up with interesting control problems. But of course, full information is highly unlikely unless the utility suddenly spins out a EV charging company. And so more likely scenarios when you have limited information, where the EVs do not share specs or objectives potentially, and the grid operator does not share its transformer measurements directly. And so you have some kind of independent coordinator, or maybe the utility represents the coordinator, And you can have individual EVs solve their own local optimization problems. You can have the coordinator effectively measure or manage its ampacity. And so you can have this broadcast of certain incentive signals or incentive schedules come out so that vehicles can adjust their local EV problems, can adjust their schedules, and you can iterate between the coordinator and the individual local problems until convergence. And so there are lots of ways to kind of prioritize the EVs effectively prioritize themselves over time, given the incentive schedules. The transformer effectively allocates capacity ahead of time so that the EVs have sufficient capacity to charge their cars. And so there are many, many ways to solve this, including, ADMM, Aladdin. We developed our own schemes in this as well. There are many ways to kind of build these distributed schemes out. But the core point here is that if you have limited information, the distributed control problem looks different, and you need to think about what information you have and what information you don't have access to. A different approach, which is instead of a top-down broadcast approach, you take a device-driven approach. In that case, you are the coordinator, the aggregator. You're depending on the devices communicating to you what their available flexibility is, and they can communicate that at any time that's convenient to them. And so you have an asynchronous implementation where devices effectively request access to the grid at certain times, or broadcast, or devices send their fitness levels, the fitness for flexibility levels at certain times. And so you as a coordinator have to effectively manage those incoming requests, potentially in real time, or you can build small queues up. And in either way, the devices here are the ones providing the coordinator with potential for control. And so that control could be based on the device's need for energy. And so you can have a probability of interaction based on the device's need for energy. So a water heater that's cold is more likely to communicate with the coordinator than a water heater that's warm because it doesn't need energy. And so you can effectively, based on the incoming command or incoming requests coming into the coordinator can build effectively a good estimate of the available flexibility. And there are lots of things you can do when you have the devices communicating with the coordinator rather than this broadcast-based approach from before, including accounting for local device constraints. Even local network measurements could be incorporated. And I'll show that in a bit. And so we implemented, as part of an ARPA-E project, a field trial with 208 loads. This was implemented using a bottom-up control architecture, and we showed that this bottom-up control architecture could effectively deliver frequency regulation services using PJM's pay-for-performance score and historical power reference signals for frequency regulation signals. And we showed that we could deliver pay-for-performance scores above 90% on 4 different days. And so this 90% is effectively better than PJM's own average system performance and effectively outperforms other assets on the grid except for megawatt scale energy storage. And so we showed that 200 loads could provide frequency regulation sufficiently high performance to outperform most generating assets. We also showed that when you have these device level schemes or these bottom-up schemes, that just by modifying the logic at the devices, you can really improve the fleet's performance. And this was some work with some colleagues at the University of Michigan, where we kind of took some of these ideas from packetized energy and we applied them to a different set of devices and effectively modified only the way in which these devices interact with the coordinator. And so instead of saying, I am available to turn on only, the devices could also say, hey, I'm available to turn off. And by doing that, you can see how when you augment the communication protocols from the devices to the coordinator, you can really improve performance by going from here to here, and from here to here, and from here to here. You can see performance improve significantly just through effectively a software update. So over the air HVAC system update. In addition to that, we've shown that we can augment not just the device's request logic, but also integrate effectively grid data or grid measurements locally into device decisions, and through some kind of traffic light logic, effectively manage a high penetration of smart loads or electrified assets across a distribution feeder. And of course, when you show you can do something doesn't mean there's any guarantees. And so doing this work kind of led to a bunch of new questions around, which measurements type should we have, single phase or three-phase measurements locally? Should we look at which locations are most salient for measurements? How often should you update your measurements? And what about noise on these measurements? So there are lots of open questions to be had, but the power of kind of a bottom-up coordination scheme is really the idea that you can augment local behavior and create a more or higher performing fleet capability. And so now that we've kind of poked into the grid data itself, the question becomes, who has access to grid data? Does the aggregator who manages devices have access to grid data, or do we need to think differently? And so an open question that I think still is open today is, what role should the grid operator play when it comes to managing these resources, when it comes to flexibility? And so you can go back, and then there are some heavy names here on like Taft and DeMartini, who looked at kind of grid architectures and have been pushing for the distribution systems to become more like transmission, to more leverage what's called enmeshing of different networks. And the core argument kind of rests on the fact that the telecom industry went from kind of these radial networks to high performance resilient networks by enmeshing them. We see today that distribution systems are still managed fairly in a radial operating scheme and could perhaps benefit significantly from enmeshing themselves, which of course requires a rethinking on how we manage distribution feeders. For example, the two blocks of resources up here, if they were to share energy in any way, there's no clear path for them to do so. And so if we enmeshed distribution networks, that path would exist. And so that kind of brings the question of, if you have a lot of resources and you aggregate them together and you then bid them into wholesale market and you're good enough and you win that bid, how do you disaggregate? And we've seen there are hundreds of papers on optimal power flows, which assume that you have access to devices, the grid, and everything at once. And we have had our own experiences kind of working with Con Edison, with Orange and Rockland, who were amazing partners and kind of teaching us about distribution system operations. And so we built effectively a project around the assumption that Orange and Rockland would manage, it would represent a utility-centric coordinator that manages all DERs, manages all network operations, and manages the market interface. And so there was a very interesting project where we kind of looked at the market exchanges between utilities and wholesale markets. We had thousands of feeders, we had millions of DERs, and we basically decomposed that operating paradigm, looking at individual feeders, and the individual feeders were composed of individual kind of DER hubs, each of which would kind of manage locally into these local flexibility zones. And so we had these local flexibility zones that could then be aggregated all the way up through the utility because the utility knows everything, the utility controls everything. And so we showed that that was certainly possible computationally if the models were there. It was possibly from a controls perspective, and we showed the whole communication interface about who, at which points is data transmitted up and downstream. And so we showed that Orange and Rockland certainly could become a utility that manages everything itself, could become its own DERMS, basically. But in doing this research, you also ask a bunch of questions. What are the limits on how much you can push through that system when you have a bunch of DERs? So being able to do it does not answer the question of how much can you do. And so what's the hosting capacity of a feeder? How do we leverage hosting capacity in a more dynamic setting? And what roles can third-party aggregators play if the utilities control everything? Or conversely, how can third-party aggregators and utilities coexist? And so that brings us back up to the asymmetry in information and control between utilities and aggregators, right? Utilities know the grid well, have an objective of managing grid reliability, but don't really have in practice access to devices, certainly not behind the meter devices. But the grid utility, the utility itself knows the capacity of the grid very well. At least they could. Aggregators, on the other hand, don't know the grid very well. Certainly don't have access to real-time data on the grid unless they have certain sensing capabilities. But the aggregators know very well what their customers need, and they know very well how they need to manage market interfaces to earn certain revenues. And so there is this oil and vinegar challenge between them. We've heard in the past about prices to devices. There has been some academic work on distribution LMPs as ways of doing things, but let me try to convince you of something different, and different in the sense of something familiar. And so if you think of internet service providers, so when I here in Burlington, Vermont, we have Comcast, and Comcast is basically the only internet service provider we have. So we pay whatever they want. And so I have 300 megabits per second at home. And that 300 megabits per second is effectively the bandwidth that I'm allocated of the internet, quote unquote, or at least of the local network. And so when things happen, the ISP manages dynamically the network and can route data packets through that network at certain efficiencies. It's a highly meshed network, of course, and so it performs very well almost all the time. And so if we think of megabits per second and convert that to power, then we can think of hosting capacity as a measure of bandwidth. And so if I have a bunch of flexible devices, if the utility could somehow determine the available hosting capacity at each node in the network, then a utility, an aggregator, could just access, with its flexibility, that available hosting capacity at any given time to access wholesale markets. And so what we're proposing is kind of a return to old, because utilities are very good at understanding hosting capacity. Maybe they don't compute in the right way, maybe they don't use real-time data, and maybe they don't update hosting capacity very often, but they know how to do hosting capacity. And so a lot of our thinking really has been around how can aggregators effectively get access to hosting capacity when it's available, and how can aggregators prioritize themselves in certain locations at certain times, effectively bidding in some way for the available hosting capacity. And so to find hosting capacity, we started looking at how do you find the boundaries of a distribution feeder's capacity? Like, how do you know how far to push a feeder to its limits? And so there's lots of work in Australia looking at operating envelopes. There's work in Michigan looking at blocking controllers, where the utility and the aggregators kind of collaborate, but effectively the utility is in charge and can block controls. And then here we're kind of looking at how do we quantify and characterize hosting capacity more dynamically. So dynamic hosting capacity, which is also a term used in the UK by certain companies. And so for us, we're looking at dynamic hosting capacity. We want to find what's the set of all possible injection profiles, and then basically figure out how to maximize that set. And so if you write down the equations, we get some grid optimization problems that are pretty fun and interesting, at least to the academic side of me. And so if you look at the equations that define the power flow for a balanced distribution feeder, which is of course not a real thing, but it's an academic thing. And so it starts to ask some interesting question initially. And so you can kind of look at the blue region is the set of all possible inputs. So in this simple node, in this simple system, we have two controllable loads, PG2 and PG3 at nodes 2 and 3. And so if I vary PG2 and PG3 across a range, I can basically see whether I'm satisfying all my current and voltage limits. And so the blue set represents the regions where I'm satisfying limits, and anything that's white means I'm not satisfying limits. And so you could chart potentially a trajectory here, A, where PG2 and PG3 achieve certain values, and in aggregate, they're basically increasing their injections, and the red path leads to a voltage violation, the green path does not. And so you can kind of question, how do I find the region which allows me to decouple decisions from PG2 and PG3? If you look at a circle, an oval, instead of a square, a rectangle, so the rectangles effectively allows PG3 to operate independently of PG2. And so the idea to compute this rectangle is to eliminate this convexity, this non-convexity. If you eliminate the non-convexity, we can effectively find the largest corner points, the black stars here. And if we have eliminated the non-convexity, we know that the underlying problem is convex. And so the two stars will be completely, the two stars will define a set of feasible solutions across the entire hyperrectangle. And so what that means is that we can, if we find this rectangle, which represents a convex inner approximation, we can effectively define hosting capacity, and we can effectively decompose the available hosting capacity at each node in the network. because we can do this everywhere in the network. And so to do this, we need to think about convexity, we need to think about optimality, and we need to think about feasibility. And so the feasible set of all possible admissible dispatch solutions is given by blue, for example. People have in the past looked at convex relaxations, but convex relaxations do not guarantee admissibility. And so if you implement a convex relaxation to get rid of that non-convexity, you can end up in the white spaces where the solution is basically exceeding voltage or current limits. And so what you need to focus on is convex inner approximations. But sitting with a curvature, having curvature means that your decisions at one node depend on decisions and actions made on other nodes. And so having effectively multiple aggregators existing in a network, we effectively have to decouple their decisions, and that requires hyperrectangles or boxes through these convex inner approximations. So we constrain the convex inner approximation to actually require certain structure. And so what's really nifty here is that we've done some work, and we can show that we can effectively find large hypercubes or hyperrectangles by eliminating the non-convexity with a lower bound and an upper bound. And we've shown that the lower bound is affine and the upper bound is convex. And so we can effectively replace the non-convexity entirely and create proxy variables that bound physical reality. And so if my proxy variable, for example, the plus V, is within the voltage limit on top, and the proxy variable V minus is above the minimum voltage limits, then I know the actual voltage will be somewhere in between. And so by eliminating the physical realities and working only in the proxy variables, I can effectively bound the physical behaviors. And I know that as long as my proxy variables are within bounds, my actual variables will be as well. And so we have some math to back that up. It relies on some nice properties of the disk flow formulation. And so it does not extend to every possible power flow formulation, but that's something we're working on. And so we can show examples here that shows that, under full load conditions, the network effectively observes this very nice convex upper bound and this affine lower bound, and in between is reality. And the same thing holds for no load conditions or any other load conditions. And so this upper bound is convex, the lower bound is convex, and we can effectively optimize both proxy sets of variables. And so we solve effectively to find the upper corner of the hyperrectangle, we solve one problem. To find the lower corner, we find the other problem. And when you combine P plus and P minus, you effectively have the entire hosting capacity. We have some math to back this up again. And the basic idea is that as long as the system operates under monotonic conditions, so adding more and more load increases the voltage, having less and less loads decrease the voltage. Same thing with currents. And so if anyone has worked on convex inner approximations or convex restrictions, they know that they're very, in general, can be quite conservative. And so we've been looking at comparing the convex inner approximations with kind of nonlinear formulations and convex relaxations. And so we can see that the nonlinear implementations and the convex inner approximations are fairly close. And so that implies that the convex inner approximations are not overly conservative, which means that it's useful. And so the approach we've taken seems to be useful, seems to not be overly conservative, and has certain guarantees that a utility who cares about reliability would care about. The fact that the grid remains reliable under any aggregator actions. And so we can take these capacities and this hyperbox, the hypercube that we're constructing, or the hyperrectangle that we're constructing from these inner approximations, represent each node in the network. And so you can weigh effectively or balance where in your network do you want flexibility, or where do you want to incentivize more flexibility than other areas of your network. And so if you're a utility, you may want to care about maximizing overall hosting capacity, or in certain areas, you may want to incentivize pockets of load in one area over others. And so through this formulation, you can effectively weigh different nodes. And so you have an n-dimensional hyperrectangle if you have n nodes in your network. And so each of those n nodes give you a P plus and a P minus, which represents the flexibility available at that node. And so you can take those hosting capacities. If you only have a single aggregator, you can basically run through this open loop, distributed and grid-aware DER control policy, where a reference tracking signal in blue which would be the market service signal for the aggregator, for example. So the aggregator receives effectively the hosting capacities from the utility, and that's the only exchange with the utility. And the aggregator then can track within that hosting capacity to deliver its market services, and maybe it tracks perfectly. And as long as it stays within its hosting capacity in green, the voltages of the resulting network are all within limits. And so here we show effectively a pretty fast cycling of a battery power, basically, to track a wholesale ancillary service or frequency regulation signal. And so you can see here that as long as you take the network aware approach, all your voltages stay within limits. If you take a greedy approach where you just track the market signal to maximize your revenue as an aggregator and ignore the grid itself and reliability, you end up exceeding voltage limitations. So this is just a toy example. And so what we're proposing and what we've worked on here and still working on is the idea that dynamic hosting capacity allows us to overcome the data and control asymmetry that exists today between utilities and aggregators. And that the dynamic hosting capacity fits neatly into kind of aggregators control architectures, certainly if the aggregators are aware of where the devices sit at any given time. And so we believe that dynamic hosting capacity can effectively capture grid conditions, grid limits on hosting capacity, and then can share that hosting capacity with aggregators who know their flexibility, who know how to manage comfort limits of consumers, who know how to manage a lot of behind the meter loads, and can effectively offer their available flexibility to consumers. And so that's kind of the end of what I promised and what I wanted to talk about when it comes to the battle between grid operators and coordinators. But I do want to just briefly highlight the idea that, you know, the real world has virtual batteries in aggregation form, but there are also physical batteries that have very interesting behaviors, certainly in northern climates. And so we're we have a new project with Department of Energy starting on hybrid energy systems, looking at both heat, PV, storage, hydrogen, power, and kind of like effectively a microgrid. And so I was inspired by a sabbatical in Denmark at DTU, where they're talking a lot about energy islands, which is the ultimate hybrid energy system. And so the idea of effectively looking at, in northern climates, what role does the cold weather play on the performance of battery PV plus hydrogen electrolyzers, for example. And so we're going to be building models, building facilities, building accelerated testing laboratories to essentially do hardware-enabled analysis and modeling, and then putting these models together into a digital twin of the hybrid energy system, but also expanding that idea to cover Vermont's transmission grid and being able to run real-time models, what-if studies, and looking at more and faster dynamics, which becomes important as we move to power electronics-based interfaces. And so the objectives of the projects are interesting. I'll skip through them, but they're not. So we're looking at long-term planning models. We have short-term operations, looking at how to develop and deliver advanced grid services across different climate conditions and across the year, and understanding how efficiency changes as the temperature drops for batteries, for example, and how PV is affected. Certainly in northern climates, that's important. And then we're going to use the platform and the hybrid energy system that we're building, the facility itself, roughly 100 kVA, to really help local community colleges looking at how can we build workforce development around these infrastructures. And we know that we're not alone in kind of looking at these questions. And so hybrid energy systems is a big interest to the Department of Energy. And there are lots of open questions that we're looking forward to tap into and kind of poke as well. And so it's just virtual batteries, physical batteries are quite interesting systems, and we're looking forward to kind of contribute to that. And I'm always looking forward to take questions, and they can be online or offline, and appreciate your patience today.
Great, thank you, Matt. So we do have a little bit of time for questions if there's anyone on Zoom.
Is there anybody on Zoom? There are chat comments.
Yeah, I don't see any questions
So
in the chat.
Can I, let me start, Matt.
Of course.
Can you hear me?
Yes. Can you hear me?
Yes. This is Maria Illich from MIT. So I I wish you were here in person because questions probably would need go from now till midnight over wine. I mean, honestly, everything is so loaded, what you said, and there are prior works, there are real open questions, there are development things, there is technology transfer. So it looks to me that what you are doing in Vermont, you are sort of combining all of the above and trying to get where. My question is, if you were to be successful with what you're doing at Vermont, how would you catalyze what? I don't know if my question makes sense.
That is a midnight question. That would be a lot of fun to discuss, Maria.
I think we will get together and talk about it, but I think the reason that I'm asking, I'm getting older, and if you think about some of these things, available transfer capability, hosting capacity, we really have not even defined rigorously because there is dynamic aspect of that support. What I'm struggling with, and I bug my students with that, is really whatever we propose has somehow to be linked to first principles. So we go to utility and say, this is for sure going to work, right? And that's another midnight question. So you're working a lot with national labs, having all these projects. What is the path to get from here to there? What's your wisdom on that?
That's a very good question. Well, it's a very hard question too, but I guess maybe I would push back and say, let me ask you a question. What will utilities look like 30 years from now?
And I answer this question again. I think that, do you remember how many people on the call remember Fred Schweppes homeostatic control?
Yes. Yep.
Homeostatic control, I think its technologies have come. He basically said, put this sensor in my washer, put this in the refrigerator, and everything is automated. And so there is this really fundamental question. If we have radial connections and so forth, do you actually need coordination by utility? Throughout your talk, you were saying you, I didn't know who was you, because you have your aggregator, you have one of
fair point. No, that's a fair point.
Right. So I think I would like to go to talk again and I watch it, but I think different questions, different sub-questions involve different decision makers.
But that's a fair point. My sense is that if you want to offer services to utilities or grid operators, you have to be able to measure them. So you have to be able to guarantee that certain services are available, and you have to be able to provide that guarantee depending on what you're providing, what grid service you're applying for, but you need to be able to have an estimate of your capability almost in real time.
So to go back to try to answer the question, if we think about parallel with telecom, I think there have been a lot of defections from AT&T. And so I'm really wondering, if at some point entities, I guess users who have a lot of renewable resources, they are natural candidates. Like in Vermont, you're a natural candidate for wind. In Puerto Rico, natural candidate for solar. To actually do something more efficient, cleaner, and still not too costly, people are beginning to sort of self-organize themselves. And so I think the very difficult technical questions are going to be the ones on, and I think you had the pictures somewhere in the middle where you have all of these decompositions. So the decompositions, when they connect and reconnect, and you were talking about radial networks being limiting, sure they are limiting, but you can change that with normally open switching, normally closed switching. And the minute you start doing that, you run into technically open questions like, you want to connect with power electronics, it goes completely blows up and stuff like that. So do we know as a community, what is a handful of real hard questions that we have to answer in order to make things move forward?
So I think opening and closing switches, so running effectively a loop scheme in distribution systems that are not already meshed. So if you look away from Con Edison in New York City, other large urban centers, They are operating as radial networks.
Yes.
And those radial networks have effectively informed all scheduling, controls, safety protection schemes, and everything else.
There is nothing in these radial networks, to the best that I know, that is online decision making and control. It's pre-programmed. So you start, and this is what differentiates really distribution from transmission. Transmission, there is a lot of sort of software-enabled online, scheduling and stuff like that. I think it's fair to say in distribution, there is nothing going online except for
I would certainly appreciate models that explore the benefits or the challenges or both associated with loop schemes. And so if we have good models, let's loop them up, let's enmesh them, and let's show, maybe academically at first, that there's value in operating the schemes in a more complex manner, especially with lots of power electronics on there.
Right. And I think this is going to manage intermittency in different parts, sort of average the load and the resources if they start reconfiguring. There is a little bit research going on that, but I think that's one key one when you want to go from these virtual power plants or virtual microgrids into having more system level effects that utility sees. The transparency, it's getting just to be too complex for utility to see everything.
So maybe what they need is better visibility and observability of their system.
They don't know what needs to be done. I think that's where academia has to jump in. What is the minimum information? We've talked about that, and we are working on that a little bit at MIT. On what is you mentioned this duration, rate of change of power, going back to some measures that that all entities understand, rather than saying frequency should be point something, right? And
so I think there's a group of academics who look very much on the dynamic elements of power systems in general, and try to look at questions from the control systems perspective. And in control systems, we have measures for designing controllers. We know how to define observability, we have controllability. We know a lot of things about dynamics and designing controllers.
For systems.
For certain systems, yeah, surely. And it would certainly be interesting to kind of see that same thinking be applied in power engineering. And that's almost like a workforce question, I think.
It really is. That's why I'm asking these questions. You were at that NSF workshop last week and so forth. I think we have to connect it with what we can prove, what we can't prove. But on the very positive side, I really am impressed with what the University of Vermont is doing. You guys are going full speed. That's why I'm asking, where are we getting? Because you have so many projects and now converting them into startups and stuff like that. What is the end goal, or there is a path somewhere?
I don't have an end goal in mind. I think it helps to be surrounded by industry in Vermont that's very open to discuss things.
Yes.
And so we have regular sit downs with transmission and distribution system operators who are doing stuff that appears, advanced, certainly from a US perspective. And so they are doing some flexible interconnections, for example, in Vermont. They are looking at dynamics, like NERC and ISO New England is pushing certain EMT requirements on transmission operators, and that's raising certain concerns. And so there's lots of questions around, can we model and guarantee certain stability conditions under high penetration of inverters? That's certainly something that's of interest. But what is the end goal? I think the end goal is to develop tools and techniques that'll help transition, whether it's renewable integration or aggregation of behind the meter resources. Basically make electrification a success, make renewable energy integration a success. And we think the interface of the main challenges there are really centered on hosting capacity and real-time control problems. And hosting capacity is an optimization problem, but it's not applying OPF as if you're a utility.
Sure.
I think OPF is a real challenge to get working in practice, but I think optimization-based techniques to promote certain resources to flex themselves is quite doable.
Well,
I think there's some other questions on Zoom. No.
Well, let me just finish. I think I would also suggest, and I think you've been leading on the national lab side, and to have more of these brainstorming things by the community, forming the community. It looks like there is a lot of rediscovering things that already are known.
Yeah.
And they're open questions, so we need some R&D agenda for this, at least at the academic level.
I mean, so we do have the technical committee on smart grids at the Control System Society.
Yeah.
If you have,
Yeah, I know. Yeah, I'm part of that.
we could certainly push those elements.
Yeah, I think we really need to know what is known, as I said, going back all the way to Schweppe with homeostatic control. And
Yeah.
It's people, nobody in my room knows actually what homeostatic.
So Schweppe's, yeah, that's true. There was a lot of good work back then.
Yeah, and so it's been brewing for a while, but I think need to put it in the context. And if we only were to answer this question, we'll do some brainstorming this fall, I promise the MIT people. So we'll have some.
Agreed. We're going to do the same thing too. So once we have the third person here, Sam, then we'll start to do some more outreach regionally and.
Yeah. Okay, I'm done. Thank you very much, Mads, for doing.
Thanks, Maria, for the opportunity.
I think that Daniel has some other people. Sorry.
Yeah, I saw Akhtar. If you want to ask a question.
Yeah. Thank you for the presentation. It was really nice. So I have actually two questions. So my first question is regarding the last part where you have the aggregated flexibility from different DERs, and then you show the blue curve, and there was a circle, like this missing part. So my first question is why we have this blank space
Sure.
In this one, and a comment on because I'm working on the similar topic. Normally, when we show the the feasible operating region or the flexibility region, we show P and Q graphs. And what was the reason that you have both P's on x-axis and y-axis? And then the next question would be, right now you are doing for aggregators and the DSO level, and the problem is bigger, so we will have to do for the DSO and TSO level. So what kind of so DSO can provide flexibility to the transmission system operator. So what kind of challenges you see over there? Yeah, so a lot of questions together.
Yeah, that's a lot of question, Akhtar. So the first question is the circular regions in the figure here.
Yeah.
So the effective, so you can only plot two dimensions in one slide, but effectively you have a high dimensional object. And when you place constraints on it, like the voltage constraints, you're slicing a region of that object into pieces. And so when you project that sliced object down into this PG2 and PG3 space, which is the dispatchable space, right? This is the space of my control actions. Then the slices of the voltage limits are what creates the holes. And so if I tighten the voltage limits, I'd be making those circles bigger. If I lift the voltage limits, I'll be making those circles smaller because the slices in the high dimensional space.
Yeah, it is opposite to PQ. When we have PQ, we are actually shortening the area. And And
the reason we're not doing, so here Q is assumed 0 because we're managing loads. And so these would be resistive loads, for example. If you add in, so we have other works that looked at adding reactive power. You get a coupling between the active and reactive power. And so if you use reactive power properly, you can expand the regions. It's very complicated to plot PQ and across multiple nodes. And so we just don't do that. But reactive power can be incorporated, like the IEEE 1547, if you're looking at inverters, for example.
Yeah. Okay. Yeah. The last question about DSO TSO coordination and what kind of challenges you see there.
And so in that scenario, I guess the DSO use its hosting capacity, not just downwards for the aggregators, but also upwards for the transmission operators.
Yeah.
Yeah, so that makes a lot of sense. I think that the question there just becomes one of when the utility makes the decision to provide those bounds on aggregations or hosting capacities or operating envelopes, the utility has to make some decision around how to prioritize certain parts of their network. So, for example, the head node versus leaf nodes and versus nodes in between. Where is that aggregate hosting capacity coming from? And how does that mesh with the available flexibility from aggregators? And so that it seems to be a doable problem, but you need some kind of iterative solution, perhaps.
Yeah. My question was actually about the information sharing. For example, in case of aggregator and DSO, we know what kind of information they have access to, and they're comfortable to share. And in terms of TSO, what would be the kind of information they would be interested to share, and what would be the kind of information they would not like to share between them?
So my guess is, Aktay, that as long as you're sharing whatever is at the interface of those substations, like the sub-transmission substations, which is the sizing of a transformer, I guess is the MVA rating of those transformers are probably known on both sides.
Yeah.
And so my guess is that as long as you stick with the operating envelopes being P's and Q's in totals, that probably would work.
Okay.
That seems reasonable.
Yeah. Okay. Thank you. Very nice presentation.
Thanks, Akhtar.
So
a
Max,
few other people in
Thank
Zoom chat as
you.
well.
Okay, go ahead.
Yeah, Dakota asked, can the theoretical results on CIA and HC that were presented be extended to unbalanced three-phase distribution systems? How would uncertainty in DER, non-controllable loads, and network parameters impact this analysis?
So that's a good question, Dakota. We believe we can extend. So we're working on extending the convex inner approximations to unbalanced three-phase distribution systems. There is some recent work looking at convex restrictions on transmission networks, which are meshed, and you can formulate the three-phase distribution systems as a meshed network. And so we think we can adapt the strategies from convex restrictions on transmission networks that are meshed to three-phase unbalanced distribution feeders. So that will be the approach we've taken. To account for uncertainty, there's kind of a dirty, quick way to do it, and then there's probably the more appropriate way to do it. So the dirty, quick way is if you build in margins. So the uncertainty of DERs could mean, for example, the availability of, I may not know whether I have exactly this much flexibility available or this much hosting capacity or this much. So there may be uncertainty in the available hosting capacity, for example. And so if your hosting capacity is uncertain, you could take a robust approach where you're basically going to say, my uncertainty is bounded, and I'm going to take worst case and guarantee that under any realization of this uncertainty, my hosting capacity is safe. And so that the robust approach would kind of be the dirty, quick way, but that assumes a bounded uncertainty, which probably is reasonable. A more appropriate one would be a stochastic implementation of this. And so that would mean a stochastic implementation of these optimization problems here, where you're, so then you end up with some kind of stochastic OPF problem, which can be cast maybe as a chance constraint problem if you know the nature of your uncertainties. So if you know your distributions, you could do that. And yeah, so the robust one seems most reasonable, at least in the short term, until we have our handle on three-phase unbalanced. The other question, Dakota, would be if you have the communication infrastructure and enough measurements being fed back from the grid, you could effectively run this as a feedback system and then use the feedback to update your hosting capacities very quickly, and then have the aggregators adapt very quickly. And so that becomes more of a dynamic problem than kind of the steady state OPF problem. That would be interesting, kind of speeding up the loop.
Yeah, looks like more question in the chat, which is from Masood. How can utilities effectively manage and allocate their dynamic hosting capacity to balance performance, cost, and scalability, and ensure they're able to meet the needs of their customers both now and in the future? We are running up on time, so I guess maybe a very brief answer to this long question.
They can't right now, they will in the future.
And so you would have to look at the formulation of your hosting capacity, and you'd have to take into account, and your objective function has to account for those things. And so that would be my answer. And I would still question whether utilities need to, how much utilities need to worry about the customers and who their customers will be in 30 years.
Yeah. So I think we are running out of time, Matt. I thank you very much. I just wanted to maybe close with one comment, that a lot of stuff that you were talking about actually was spearheaded and visioned by ARPA-E Nodes program.
That's
and,
right.
Really, you know, our hats off. We all were part of that, and I think it's if we had more programs like of that
Yep.
type continuing. So,
Yeah, I agree. That is one thing I wish the DOE would focus a little bit more on, because even though Node was fabulous, we didn't solve all problems at once.
yeah. So,
Are you proposing to run as a program director, Maria?
I was approached, but I am too old for that. So, and I have things to do at home. So,
I see.
thank you very much, everybody on the remote. I think there were a lot of people. So, Matt, come sometimes and let's just continue.
For sure.
Right?
For sure.
Okay.
See you all.
Bye-bye.
Bye.